4 variables simultaneously. So for example, the relationship between gender, race, and college graduation. Next slide, please. Now, the 5 basic steps. So I know there's a little bit of overlap between us and the last group, but I shall continue. Firstly, central tendency. Okay, the central tendency is the tendency for values of a random variable to cluster around its mean, median, or mode. So the central tendency, like any other basic steps, are used to characterize the data. The 2 types of variables that we can characterize are discrete and continuous. Next, moving on to the spread. The spread, in probability theory and statistics, variance is the expectation of the squared deviation of a random variable from its mean. So informally speaking, it measures how far a set of numbers is spread out from their average value. The variance has a central role in statistics, where some ideas use it, including descriptive stats, statistical inferencing, hypothesis testing, goodness of fit, and even the Monte Carlo simulations. The standard deviation, on the other hand, is simply the square root of the variance and is a measure of how spread out the data is. So to calculate the variance, you would first need to work out the mean, which is a simple average, and then for each data point, you subtract the mean and the squared result, that is the squared difference, and then you work out the average of those differences. So next, I'm going to talk about skewness, which refers to the distortion or asymmetry in a symmetrical bell curve or normal distribution in a set of data. Of 0, while a log normal distribution, for example, would exhibit some degree of right skew. A positively skewed bell curve means that it's skewed to the right. That is, the data would contain some extreme positive value. So a very high positive outlier, which would be pulling the tail and causing fatter tails and the distribution of the curve to be such. A negatively skewed simply just means the opposite, that the data would contain a highly negative outlier. The mean of a positively skewed data set will be greater than that of the median, and the opposite would be true for a negatively skewed data set. Skewness is used along with kurtosis to better judge the likelihood of events falling in the tails of the probability distribution. So, for example, in finance, investors, would note the skewness when judging a return distribution, because it would consider extreme values rather than just focusing solely on the average. So, for like short-term and long-term investors, there'll be a little bit of a difference, because they would need to consider extreme values rather than just the average, because they're likely to hold a position long enough to be confident that the average would work itself out. So investors commonly use standard deviation to predict future returns, but standard deviation assumes a normal distribution. Next, the covariance. The covariance is basically the joint variability of 2 random variables. So it measures the directional relationship between the returns of 2 assets, for example. A positive covariance means that the assets' returns would move together, and negative, of course, means the opposite, which means it moves inversely. A covariance basically is calculated by analyzing the standard deviations from the expected returns, or either that or by multiplying the correlation between the 2 variables by the standard deviation of each variable. So the covariance, it's a significant tool that we use today in modern portfolio theory. And it's used to ascertain what securities you can put in a portfolio. And risk and volatility can be reduced in a portfolio by pairing assets that have negative covariance. So covariance evaluates how the mean values of 2 variables move together. For example, if stock A's return moves higher whenever stock B's return moves higher, and the same holds true when the stock returns decrease, then the stocks are said to have positive covariance. So in finance, covariance are calculated to help diversify security holdings. For example, in CAPM, beta measures the volatility or systematic risk of a security in comparison to the market as a whole. It's a practical measure that draws covariance to gauge an investor's risk exposure specific to one security, for example. And correlation, on the other hand, is a degree. It's a measure of the degree to which two variables move in relation to each other. So it's computed as the correlation coefficient, which must fall between -1 and 1. The correlation measures association, but does not show that X causes Y or vice versa. So in fact, it doesn't even show whether the association is caused by a third unseen factor. So basically, it does not prove causality. Perfect correlation of one means that one security moves either up or down, the other security would mirror that movement. So now, conditional distribution. So conditional distribution is a probability distribution for a subpopulation. It shows the probability that a randomly selected item in a subpopulation has a characteristic that you might be interested in. So it is the probability that event A occurs and had a relationship with one or more events. So a simple example would be a box of marbles that contains 5 red marbles and 5 blue marbles. So what would be the probability of choosing a red marble? And what would be the probability of choosing a red marble given you have chosen a blue marble in the first draw? So if you're to choose on the first draw, the probability of getting a red or a blue would be 50-50. However, on the second draw, if on the first draw you got, let's say, a blue marble, for example, this means that there are 9 marbles now left in that box, out of which 4 are blue and 5 are reds. So the probability of you choosing a red marble now is 5 out of 9 and approximately 56%. Next slide, please. So now the limitations of central tendency. This is actually a humorous example, I would say, involving a statistician who drowned in a river that was only, as he calculated, on average 3 feet deep. So this theory is called the flaw of averages, which is, in fact, one of the cornerstones of Murphy's Law. What can go wrong does go wrong. Presents if we base the depth of the water simply on the average alone, we would end up drowning. And next, I shall pass it on to Shalfei to talk to you about inferential statistics.
Okay, thank you, Darshan. The next part we're going to talk about is on inferential stats. So basically, we're going to show you an example of hypothesis testing. We're going to tell you what's p-value and its significance level. I'm going to tell you what is type 1 Tapler error and how can we improve them. And at last, we're going to give you some general ideas on the central limit theorem. So first up, one of the example for hypothesis testing we want to show you is a courtroom example adopted from Wikipedia. So basically, the example wants to find out the judgment in the court trial. We want to find out if the defendant is really guilty. So then we're going to conduct a hypothesis testing under the idea that the defendant is presumed to be innocent until proven guilty. So that actually gives rise to the null hypothesis, which is the original idea, which the defendant is presumed to be innocent. So the alternative hypothesis goes the otherwise, which the defendant is guilty. So we set the significance level alpha to 5% in order to find the p-value to this hypothesis testing. So what exactly does the different component mean in a hypothesis test? So first up is confidence level and p-value. Confidence level is a range of values that's likely to contain an unknown population parameter. So before that, we mentioned the significance level alpha. The confidence level actually equals to 1 less the significance level alpha. So if you draw a random sample many times, a certain percentage of the confidence intervals will contain the population mean, and this percentage is the confidence interval. So what is p-value? A p-value is a measure of the probability that the observed difference could have occurred just by random chance if the null hypothesis is true. So if the p-value is smaller than alpha, it means that original idea, H0, is wrong. So we reject the null hypothesis. And the smaller the p-value is, the more evidence we have that the null hypothesis is wrong. So a smaller p-value will indicate a higher significance level to the test result. So on contrary, if the p-value is greater than the significance level, it means the original idea is right, then we accept the null hypothesis. Next up, during the hypothesis testing, there are always possibilities that we make some mistakes or there are errors involved. So there are two types of errors: when the null hypothesis is true, when we reject the null hypothesis, or the null hypothesis is false when we accept null hypothesis. So the type of error is the rejection of a true null hypothesis, which is also called the error of commission. And type 2 error is the non-rejection of a false null hypothesis, which is called error of omission. So how exactly can we improve these two types of errors? Type of error is aroused by the significance level alpha, and alpha is usually set to be 5%. So in order to improve or reduce the type of error, we can adopt a more stringent approach to setting the alpha level to a smaller value. As for type 2 error, it's induced by the power of test beta. So to reduce the type 2 error, we can either increase the test sample size or to relax the alpha level. So this actually reminds us of the trade-off effect between type 1 and type 2 error. So the effort of reducing one type of error will generally result in increasing the other type of error. So the key is to find the optimal level between these two. And last, we want to mention the general idea of central limit theorem. So CLT mentions that under many situations, when the population is distributed in any way, even completely random, and if we take a sufficient number of samples, the distribution of the sample means tends towards a normal distribution. So this central limit theorem is actually a key concept in the probability theory because it helps us to conduct the statistical methods that works for normal distribution with a population that has other type of distributions. So this is a general idea on the inferential stats. Now allow me to pass my time to Simon for statistical tests.
Okay, thank you, Xiaofei. Next slide. Yes, so after looking at the distribution of the data and perhaps conducting some descriptive statistics to find the mean, the median, or the mode, it's time to make some inferences about the data. And as Xiaofei previously mentioned, inferential statistics are the set of statistical tests that we use to make inferences about the data. So these statistical tests allow us to make inferences because they can show us whether an observed pattern is due to intervention or chance. So there's a wide range of statistical tests. The decision of which statistical test to use depends on the research design, the distribution of the data, and the type of the variable. In general, if the data is normally distributed, parametric tests should be used, and I think that's mainly where we've been focusing on the class. But if the data is non-normal, you can use a non-parametric test as well. So what does the statistical test do? The statistical tests work by calculating a test statistic, which is a number that describes how much the relationship between variables in your test differs from the null hypothesis of no relationship. So it then calculates the p-value, the probability value, which Xiaofei just mentioned. And if the value of the test statistic is more extreme than the statistic calculated from the null hypothesis, then you can infer a statistically significant relationship between the predictor and the outcome variables. If the value of the test statistic is less extreme than the one calculated from the null hypothesis, then you can infer no statistical significant relationship between the predictor and the outcome variables. So the assumption made in statistical testing is that homogeneity of variance or homoscedasticity, which is the size of the error in prediction, doesn't change significantly across the value of the independent variable. So if you look at the chart down to the left, you can see the far left is sort of what we want. We don't want to see a shape in the noise. We just want to see random noise. And the problem if we have heteroscedasticity is that OLS, or ordinary least squares, assumes that all residuals are drawn from a population that has constant variance, i.e. homoscedasticity. So the second assumption is the assumption of independence of observations. So the observations in the data set were collected using statistically valid methods, and there are no hidden relationships amongst the variables. An example of that could be autocorrelation. And then the third assumption is the normality of the data, that the data follows a normal distribution. So we can move on to the next slide, please. Yeah, so there's a bunch of different statistical tests that we can use. We can focus on, for example, the comparison of means, and that's the test that look for the difference between the means of variables. So that's for a small sample, it could be a t-test, large sample a c-test, the ANOVA could be a difference of mean. We can also be looking at correlational tests, where that look at for the association between the variables. That can be the chi-square test, Pearson's correlation. We can look at a regression statistical test, which tests if change in one variable predicts change in another variable, and that's the simple and multiple regression. And then we also have the non-parametric test, but I don't think we're going to get into that now. So next slide, please. So one way to see how, I'm just going to try to make my screen a little bit bigger. One way to see how to choose which test to use, we can build a flow chart. So if we start on the top, you can see if the predictor variable is a categorical or quantitative variable. If it's a categorical, then you look at, okay, what's the outcome variable? Is it categorical or quantitative? If that is categorical, then you can use chi-square. If it's quantitative, you can use the comparison of the mean test. And then you have to know, okay, how many groups are being tested. If there's 2, then t-test. If there's more, then again, you need to see how many outcome variables there are, etc., etc. Okay, move on. So in terms of t-tests, we have different types of t-tests. We have the one sample, which is the t-test that examines whether the mean of the data from one group differs from the pre-specified value, or you have the two sample t-test, which helps you decide whether the means of 2 separate groups of data significantly differ from one another, or you have the paired t-test, which you use when you survey one group of people twice with the same survey. This type of t-test can show you whether the mean has changed between the first and the second time you took the survey. So next slide, please. So just as an example, we can use the 2 sample t-test, and in order to calculate that, you have to go through 4 steps. The first step is to calculate the tested t. P is the test statistics, and x1 is the mean of value for sample 1, x2 is the mean of value for sample 2, n1 is the number of people from the first sample who provided a response, and 2 is the number of people from sample 2, and then you have sx1, x2 is the standard deviation, and the standard deviation formula is the one below. And then step number 2 would be to calculate the degrees of freedom, which is the number of independent pieces of information that we take into account when calculating the estimate. And since we're conducting a 2-sample test, the degrees of formula is slightly different from the 1 sample. And the paired Degrees of freedom is basically the number of different ways mean could vary. So step 3 would be to determine the critical value, and that represents a threshold at which the difference between the two values should be considered statistically significant. So you can find the critical value in a t-distribution table, for example, that you see on the right. You can also find it on a calculator or using Excel. So yeah. And if there's no specified alpha level, you can always use 5%. I think that's pretty decent. So the fourth step is to compare the t-statistic to the critical value. And if the t-statistic you obtain using the formula above is greater than the critical value, the statistical difference may be considered significant. And if it's lower, it may be statistically insignificant. So we can jump to the next slide. I'm trying to be quick here. Yeah.
I tried to read it out.
Yeah, I know. I'm trying. Yes, and maybe since we shouldn't talk too much about regression, I'll just should I just skip this, Prof? This is about regression.
Sounds good. This is
okay. Then we
3.
skip to the last part.
In the last part, we are going to talk about how to realize some of the statistics tests using Python. Next, please. To find the summary statistic of a given NumPy array, we can use the NumPy function below. All the function only need array parameter except NumPy.percentile. Percentiles between 0 and 100 inclusive need to be typed in as the second parameter. To explore the relationship between two arrays, we introduce NumPy.cov and NumPy.coef. NumPy.cov will estimate the covariance matrix. The covariance matrix element CII on the diagonal is the variance of data I. The covariance matrix element Cij would be the covariance of data I and data j. We can extract covariance using the codes on the right. For correlation coefficient, it's nearly the same thing. We just use NumPy.coef instead. Next, please. For Bootstrap, the point is to estimate the distribution of the statistic of interest, for example, the ratio of variance and mean. When there is no analytical form or normal theory, Bootstrap sample is the resampled area of data, while Bootstrap replicates are statistics computed from the resampled areas. We can generate two functions to find Bootstrap replicates. BS_sample is generated using NumPy.random.choice. It can help us draw a random sample from actual data with replacement. The first parameter is the array, and the second parameter is the size, which can specify how many samples we want to take out of the array. In this function, sample size is the number of observations of the actual data, so we use len bracket data. In the second function, firstly, we use NumPy.empty to initialize an array called BS replicates of size that will hold all of the Bootstrap replicates. Next, we write a loop that range solver size and compute the replicates using Bootstrap_replicate to generate that generate before and store the replicate in the appropriate index of BS_replicates. The confidence interval can be found using NumPy.percentile. If the confidence level is 95%, we can compute the 2.5 and 97.5% Bootstrap replicates. There are two ways to find p-value. The rationale is to find the probability of obtaining a value of your test statistics that is at least as extreme as what was observed in the sample. Mean can change to other functions like variance. Next, please. The permutation is used when simulating the hypothesis that two variables have identical population distributions. On the left side of this slide, we use function permutation_sample to generate permutation sample. Firstly, the observations of two data sets is pooled. This is constructed by concatenating the arrays together. Secondly, we randomly permute a sequence using NumPy.random.permutation. It can scramble the contents of the concatenated array, and then taking the first N1 entries as the permutation sample of the first array, and the last N2 entries as the permutation sample of the last array. To generate the permutation replicates, it is useful to have similar function in Bootstrap. The function is on the right side of this slide.
How many more slides do we have? It's about time to wrap up.
Yeah. Just one more. Yeah.
Okay.
Next, please. Yeah, so when doing hypothetical testing to compare the mean of two given samples and the sample sizes, if the sample size is less than 30, it is better to use t-test than z-test. To do a t-test, we introduce scipy stats. The spiral function is used to find the p-value. The first argument is t-value, and the second argument is the degree of freedom. Then we can use t the interval to find the endpoint of the range that contains 1 minus alpha% of the distribution. The parameter is in the slides, and that's all of our presentation. Thank you for listening.
All right, thank you very much. So when we talk about t-test, this is not the only way to do t-test. There are actually simpler method you can call. They will automatically calculate the t-test for you. Test of difference or test of univariate difference. All right. Now, let me just recap what has been shared with you. Now, when you do hypothesis testing, what is the thing that you want to know? You want to basically make inference about what? About the sample or about the population? On the sample you have. You need to know the distribution, at least the sampling distribution of your test statistics. And this depends on what kind of test statistics that you are using. And each of these test statistics would have an underlying distribution. And this distribution links to what you have learned in the section on distribution. Most of the time, we are dealing with what? We are dealing with normal distribution. But normal distribution come in different shapes, right? Remember, we have z-stats. Z-stats and t-stats, what is the difference? When would t-stats converges to z-stats? The difference between t-stats and z-stats is really on the degree of freedom, right? When you have enough of the sample, if your sample is large enough, t-stats is going to converge towards z-stats. So when you're dealing with small sample, you're better off using t-stats to make inferences. But you need to know the sampling distribution of your test statistics. And your test statistics is not just t-stats, z-stats. It can be f-stats, chi-square stats, and a bunch of many different test statistics. But you're making an inference about the population based on your sample, according to what you understand of the sampling distribution of your test statistics. Because from the sampling distribution, assumed sampling distribution of your test statistics, you can do inferences like hypothesis testing, point estimate, confidence interval. Now let's go to the example quoted from Wiki, judge. Now if you are a judge, which error is more serious? Type 1 error or type 2 error? By the way, what is type 1 error in this context, being a judge? Any volunteer? Or maybe someone from the group? Presenting group?
Excuse me, bro. I'm so sorry. We will be covering this point in our presentation. So maybe.
Oh, okay. So maybe Anna's team can elaborate on this. Okay? So let me just move on to touch on another point. Can you go all the way to the statistics? Meaning the first deck? The mean, the variance, the covariance. Okay, never mind. So I just want to link all the different statistics to finance. Now, when we talk about mean of asset return, this is important to you, right? Because in combination with standard deviation, you can calculate the line of Sharpe ratio, your risk-reward ratio, right? Now, how about the line of skewness? Now, skewness is actually a very important concept in portfolio management. Why? Is it good to have positive skewness or negative skewness in your portfolio? And what are the implications of having negative or positive skewness in your portfolio? Now, let me talk.
It's
Yes,
better to have positive skewness, Prof.
positive skewness. Can you explain why?
Because that means there will be a lot of small numbers and one or two extremely high positive values. So if
Okay.
you're a long-term investor, for example, you have the chance of getting a very, very high payout. On the other hand, if it's a negative skewness, it's dangerous because you will have a lot of low positive values and one really, really high negative outlier. So you can, in fact, crumble your entire portfolio.
There is a price to pay for both strategy. Generally, at least for my own portfolio, I try to design it with a bit of positive skewness. Now, when you have positive skewness, yes, you are going to potentially enjoy big returns, but on normal days, you are going to constantly make small losses. This is a bit like your momentum trading strategy. When you successfully ride on a wave, for example, if you were to use momentum trading strategy, you would have chosen the like of Zoom to invest. So this would be example of really positive return. But when you follow momentum, you also tend to make a lot of small losses on normal days. Okay, so this is the kind of return that you bear when you have positive skewness. And the most positive skewness you have, the more serious this return is going to be. More losses on usual days, but sudden jump in your portfolio on less commonly so, but you will have big returns. Now let's talk about the other scenario. The other scenario will be negative skewness. Negative skewness means on most days you are going to enjoy a tiny positive profit, but there will be days in which suddenly you will suffer a big drop in your portfolio return. Now, give me some examples of what you have seen in the real world or trading strategy. One trading strategy is basically your carry trade. Have you learned about carry trade? Carry trade is one in which you borrow money from, let's say, Japan, where the interest is very low, and then you invest the money, you convert it in, for example, Aussie dollars, and you invest it in Australian deposits. Australian deposits, I think, is around, 4%? So you borrow at zero interest, and then you invest and you get 4%. So you earn the spread. So on most days, if the currency fluctuation is very minimal, you earn 4%. But there will be times suddenly carry trade unwind and the interest suddenly jump. This may wipe off all of your profit in the year. So this is another example of negative skewness in the portfolio. And have you heard of LTCM? LTCM is run by Nobel Prize laureate. They have been very successful. But one fine day, due to the Russian ruble crisis, the entire firm suddenly crashed and went under. So this is another example of having too much negative skewness in your portfolio. So most days you are going to make a positive return, but it just takes one big, black swan event for the entire portfolio to be wiped out. Okay, so that's the implication on finance. Now let's talk about covariance and correlation. Now, you have learned this in Markowitz mean variance optimization, right? So how do you construct a portfolio that would maximize the benefit of diversification? You basically sum up the covariance for every single pair in your portfolio, right? So what matters when you have enough of components or constituents in your portfolio is really not the variance of the contribution due to the variance of each individual stock, but the covariance of that stock with the rest in the portfolio. Okay? And if the correlation is 1, there's no diversification benefit. But if the correlation is -1, you have maximum diversification benefit. Okay? So this is how you put into context all the basic stats in finance. Now let's move on to the next group. Next group, as and when you're ready.